Welcome to the second lecture in EE404 of this week. In the last lecture, we have started with obtaining phase-plane trajectories of second-order systems. In the general case, we are going to consider nonlinear systems, but we are first going to look at the phase-plane trajectories of linear systems, and then we will make them, we will use them as a basis for the phase-plane trajectories of nonlinear systems around equilibrium points. So the first thing that we are going to do is to investigate phase-plane trajectories of linear systems, and then we are going to use that theory to be able to investigate the trajectories of phase-plane trajectories of nonlinear systems around their equilibrium points. So let us write phase-plane analysis. Sorry. Phase-plane analysis of linear second-order systems. Well, in this case, we are considering x dot is equal to ax when x is in R2. Okay, so that is a second-order system. State is two-dimensional, and that means that our A is going to be in R2 by 2. In investigating the linear systems, we are going to make an assumption, and the assumption is going to be that this A has two linearly independent eigenvectors. Okay, so that is going to be our main assumption. Let us write this. And we are not going to consider any other case. A has two linearly independent eigenvectors. Okay? This is unfortunately not always the case. So I can give you two matrices. So let us say that 1, 1, 0, 1. This is identity matrix, obviously. So let me say that this is A1, and let me say that this is A2. 1, 1, 1, 0. All right? So in the general case, when you look at these matrices, you see that their eigenvalues are both 1. Okay, so when I look at the if you have a diagonal, an upper triangular or lower triangular matrix, its eigenvalues are given by the diagonal elements. This is a diagonal matrix, so eigenvalues lambda 1 is equal to lambda 2, and that is equal to 1. Okay, this is an upper triangular matrix, so the diagonal elements would give its eigenvalues lambda 2 equals to 1. On the other hand, when you look at the eigenvectors of these matrices, the identity matrix, you can always find two linearly independent eigenvectors. One can be 1, 0, and the other one can be 0, 1. On the other hand, when you look at this matrix, for this specific case, you can find only a single eigenvector. Okay, so you cannot find any other linearly independent eigenvector for this matrix. Actually, any non-zero vector is an eigenvector of an identity matrix, so I can find other sets of eigenvectors for the same matrix. For example, E1 is equal to 1, 1. E2 is equal to 1 minus 1 is also another set of eigenvectors for the same matrix. Okay, and here I can take any two linearly independent vectors in R2, and those would be the eigenvectors of A1. All right, but for A2 this is not possible. So any eigenvector of A2 would be a scalar multiple, a non-zero multiple of this single eigenvector. Obviously, this is also another eigenvector, so I can write E1 is equal to 2, 0. As long as the coefficient is not equal to 0, any multiple of this eigenvector is an eigenvector. Okay, but you see that this eigenvector that I have found is linearly dependent with the first one. So for such a matrix, I can never find two linearly independent eigenvectors, although the matrix size is 2 by 2, and although the matrix has two eigenvalues. All right. So unfortunately for some systems, for some A matrices, we would have this case. And in this course, we are going to neglect completely this specific case. So we are not going to consider this case. But I can actually tell you the specific case where this can happen. This type of insufficient number of eigenvectors case, it always happens when the eigenvalues repeat themselves. So here I have two eigenvalues at the same place, repeated eigenvalue case. Both of the eigenvalues are 1. This type of case can only happen. The insufficient number of eigenvectors would always insufficient number of eigenvectors case would always happen when we have repeated eigenvalues. If the matrix eigenvalues are not repeated, for example, if I had 2 here instead of 1, then the matrix eigenvalues would not have repeated, and I would be able to find 2 linearly independent eigenvectors for that matrix. Okay, so but you see that when the eigenvalues are repeated, this really doesn't have to happen all the time, because in this case the eigenvalues are also repeated, but I can find 2 linearly independent eigenvectors. Okay, so there is only one-sided implication. If the matrix has insufficient number of linearly independent eigenvectors, then you can say that the matrix has repeated eigenvalues. But if the matrix has repeated eigenvalues, this really doesn't mean that that matrix is going to have less number of eigenvectors than its size, because here you see that the matrix eigenvalues are repeated, but I have 2 linearly independent eigenvectors, but here the matrix eigenvalues are repeated, but I have 1 linearly independent eigenvector only. Okay, so there is only one-sided implication. If the matrix has less number of eigenvectors than its size, then that matrix should be a matrix with repeated eigenvalues, but the reverse implication is not correct. So in this course, when we have repeated eigenvalues, we are only going to consider this case. Just as an exercise for you, look at this matrix, A3, 1, 2, 1, 0. So as soon as I change this 1 to 2, I actually change the eigenvalues to 1 and 2. So lambda 1 is 1, lambda 2 is 2. Check the eigenvectors of this matrix. You are going to be able to find 2 linearly independent eigenvectors, one for lambda 1 and the other one for lambda 2. Okay? So you will never encounter this situation when the matrix has distinct eigenvalues. All right? So this is our assumption. A has 2 linearly independent eigenvectors. Then we can actually try to obtain a general theory for being able to draw the phase plane trajectories of such systems. So the first thing that I'm going to do is to define the eigenvalues. D of S is called the characteristic polynomial of the matrix S, and that is also defined as determinant Si minus A. Okay? In general, if the matrix has size 2, then we are going to have S minus lambda 1, S minus lambda 2 here. And lambda 1 is the first eigenvalue, and lambda 2 is the second eigenvalue. Now, the first thing and how are the eigenvectors defined? So we say that a vector EI is an eigenvector for the eigenvalue lambda I if it satisfies this equation and if it is non-zero. So eigenvectors are non-zero vectors that would satisfy such an equation. So you see that obviously the zero vector EI would satisfy this equation all the time. Okay? But we don't call it as an eigenvector. Eigenvectors are non-zero vectors which would satisfy such an equation. In general, I'm going to be writing this equation as follows. A EI minus lambda I EI is equal to 0. And I will take EI parentheses here. In EI parentheses, I have A minus lambda I identity is equal to 0. Okay? So this actually tells us that EI is a non-zero vector that is going to give me 0 when I multiply it with this matrix. So the vectors that would satisfy such a relationship are said to be inside the null space of the matrix A minus lambda I identity. Okay? And here, null space of a matrix, null space of A, of any matrix is the vectors x such that AX equals to 0. Okay? And here, since I have this relationship, EI is going to be inside that set, null space of this matrix, and EI is going to be a non-zero vector. Okay? So we have these conditions. This is going to be how I am going to find the eigenvectors of a matrix. Okay, I am not going to use this equation, but instead I'm going to use the equivalent equation in this form. All right, that is going to give me the eigenvectors in an easier way, at least for me. So you will see. So the first thing that I would like to talk about is what is special about an eigenvector. So let us try to understand this. So suppose that this is my two-dimensional phase plane, x1, x2, and suppose that these are my eigenvectors. Suppose that I first put the first eigenvector here, and let me say that this is my second eigenvector, E2. Okay? Now here is what I would like to do. I will draw some lines here, passing on top of the eigenvectors. Right? This is the line corresponding to first eigenvector. Actually, this is called the one-dimensional space corresponding to the eigenvector 1. And this is going to be the one-dimensional line that would correspond to the second eigenvector. Okay? Now suppose that I have this system, x dot is equal to ax. Okay? Now I would like to understand what happens if I start my system, if I choose my initial condition x0 in the following way. Suppose that I choose my initial condition just like as the eigenvector, okay, E1. So this point is my initial condition, okay? I have a second order linear system like this, and I start my system exactly at the eigenvector, okay? In that case, what is going to happen? So how would the trajectory of this system behave when I start my system here exactly on top of the tip of the eigenvector? Okay? So here is what is going to happen. We know that x dot is equal to, when I have a system x dot is equal to f of x, this equation means that the velocity of x is f of x. So here I see the same thing in the linear relationship. X dot is equal to ax tells me that the velocity of x at some point is going to be given as a times x. Okay? So when I start the system at this initial condition, what is going to be the velocity of the system at time 0? So in which direction is this state going to move? That is the question that I'm asking. Obviously it is going to be a times x0, okay? And x0 is E1, a times E1, and that is going to be lambda 1 times E1, okay? By the eigenvector eigenvalue equation here. So now what does this tell me? This tells me that the initial velocity of the state, when I started here, initial velocity of the state is going to be a scalar multiple of the same eigenvector. Okay? and the scalar coefficient is just the eigenvalue, right? So now suppose that lambda 1 is real, this is an assumption, and suppose that lambda 1 is positive, okay? In that case, what can you say about the direction of the motion of the state when I started here? You can say that, suppose that lambda 1 is real and positive, then the direction of the state is going to be exactly on the same line as the eigenvector here, okay? So this is going to be my velocity. Lambda 1 times E1 is going to be my velocity vector when lambda 1 is real and positive. When lambda 1 is real and negative, my velocity direction would be pointing towards the origin exactly on the same line. Okay? So I assumed here lambda 1 is real and positive, so my velocity vector is going to be pointing on the same line as the eigenvector. But if the eigenvalue was negative, in that case, my velocity would be pointing towards the origin on the same line. Okay? So now here what happens? The velocity of the state points in the same direction. That means that my state vector is going to go in this direction, and it's going to reach some point here in an infinitesimal time interval. Okay? But here you see that this point, always this new point, has to be always on this line that where the eigenvector lives. Okay? So the trajectory of the state can never leave this line, because the velocity is always going to point the trajectory to remain on this line. Okay? So the state is going to move here. It's going to come to this point. But that point is nothing but a scalar multiple of E1. So let me say that this is x of epsilon in an infinitesimal time interval. X of epsilon is going to be alpha times E1, where alpha is going to be a very close number to 1. Okay? In this case, alpha is slightly larger than 1. It's real and slightly larger than 1. In this case, when we come here, what would be the velocity of the state? So what would be x dot of epsilon after an infinitesimal amount of time passes starting from time 0? In that case, that is going to be a times x of epsilon. So whatever the state, when I multiply it with a, I get the velocity. Okay? In that case, I would have a times alpha times E1, and I can take this alpha outside, and I would have a times E1, but a times E1 is lambda 1 E1. Okay? So you see that our velocity is again, so this is a number slightly larger than 1, and this is a positive number. So the velocity is again pointing in the same direction as E1. Okay? So in that case, our state is going to come here a little bit like this, and it's going to reach this point. But you see that point has to be again on the same line as the eigenvector. Okay? So however long time interval we increase the time here, the state will always remain on this line for all time instants. All right? Whatever we do here, if I start the state exactly on the eigenvector, then the state is going to remain on this line, and it's going to diverge towards infinity. If lambda 1 is positive, it's going to diverge towards infinity on this line. Okay? If lambda 1 was negative, in that case the state would converge to 0. Okay? Because the velocity would be always pointing in that direction towards the origin, and once we reach the origin, the state is going to remain there. Why is that? Because for this system, x equals to 0 is always an equilibrium point. And when we reach x equals to 0, the state is going to remain there. Okay? So the motions on these lines of the system would be very, very important for us. And we say here that if I start the system somewhere on this line, the system state would always remain on this line. It would always move somewhere on this line. It would be either going towards the equilibrium point at the origin if lambda is smaller than 0, or it would diverge towards infinity if lambda 1 was is larger than 0. Okay? What about the other eigenvector? It is the same case for the other eigenvector. So why did this happen? This happened because eigenvectors are vectors which do not change their directionality when you multiply it with the matrix A. Okay? Here, our system tells us that the velocity of x is going to be a times x. So whatever the x value for the system, if I multiply it with a, then I'm going to get the velocity of x. But you see that if I choose my eigenvector or any scalar multiple of my eigenvector as my initial state, then in order to calculate the velocity, I'm going to multiply that constant multiple of that eigenvector with a. But multiplication with a will not change the directionality of the state here, because it's going to have the same direction as the original state direction here. Okay? So as a result, if I consider the line of an eigenvector, line corresponding to an eigenvector, and the other line corresponding to the other eigenvector, whenever I start the state on anywhere on these lines, the state trajectory would always remain on this line. So in some way, these eigenlines, that I can call them, are some invariant lines. And when I start the system, whose meaning is that when I start the system anywhere on these lines, the whole motion of the system would remain on these lines. Okay, that is the property of these eigenlines here. We have to be careful about those. So I would like to write this fact actually. So I can write this as this. If the system is, sorry for this. If the system is started at x0 equals to alpha times E1. So if the system is started at a scalar multiple of the eigenvector, the trajectory becomes x of t is equal to beta t times E1. The same eigenvector times a time-varying function. All right? In other words, the trajectory never leaves the line corresponding to the eigenvector. So let us try to understand this. So suppose that I have x of t is equal to beta t E1. And suppose that x0 is alpha E1. x0 is alpha E1. Then these two equations therefore has to be satisfied. So when I substitute t equals to 0 in the first equation, it has to give me the second equation. If I substitute t equals to 0 in the first equation, what does it give me? So I have x of 0 is equal to beta 0 times E1. So here I understand that beta 0 is alpha. Okay? And I know that such a function should satisfy the differential equation of the system. So x of t is equal to beta t times E1. And I know that x dot is equal to a times x for this system. So this function has to satisfy this differential equation belonging to the system. Okay? So let us calculate x dot. X dot is, here E1 is a constant vector, it doesn't change with respect to time, and beta is a function of time, so it's going to be taken the derivative of. So I have beta dot of t times E1. This is equal to a times x. X is this, beta t E1. Okay? So this is going to be, I can take beta t outside, because it's a scalar function, and I have a times E1, and a times E1 is lambda 1 E1. Okay? So here we get the following equation. Beta dot of t, E1, is beta times lambda 1 times E1. Okay? But this E1 is a non-zero vector. If a multiple of the non-zero vector is equal to another multiple of the same vector, same non-zero vector, then their coefficients should be equal. So this tells me that beta dot of t is equal to lambda 1 beta t. The coefficients should be equal. And I know what beta 0 is. Beta 0 is alpha. So now I can solve these differential equations to calculate what beta of t is. You see that beta satisfies a differential equation, a scalar differential equation with the coefficient lambda 1, and beta 0 is alpha. So the initial condition is given, and I have x dot is equal to lambda 1 x. So we know the solution of such a differential equation. It's going to be the initial condition alpha times e to the lambda 1t. Okay? This is beta t. So I can substitute it back here in this solution, and that is going to be alpha e to the lambda 1t times E1. Does it satisfy this initial condition? x0 equals to alpha E1. Yes, substitute t equals to 0. And this is going to be 1. It's going to give me alpha E1. And we have seen that it also satisfies this differential equation. So just take derivative with respect to t, and it is going to be, and then it's going to be lambda 1 times this function, and multiply the same function with a. A times E1 is going to be lambda 1 times E1. So this function is going to satisfy the differential equation as well. So you see that the motion on this line is given by alpha times e to the lambda 1t times E1. Suppose that alpha is positive. So we start the system somewhere here. If alpha is positive, the initial condition is going to be alpha times E1. So we're going to be somewhere here on this line. If lambda 1 is positive, I see that this exponential is going to grow. So the state is going to go in that direction forever. Okay? The coefficient of E1 is going to get larger and larger if lambda 1 is positive. If lambda 1 is negative, in that case I see that the state is going to converge to 0, because this exponential is going to decay to 0, and at the end, at the infinity, we're going to converge to the origin. What would happen if alpha is negative? If alpha is negative, then that means that we initiate the state somewhere here. Because if alpha is negative, I am starting the state at alpha times E1. And if alpha is negative, we are going to be starting the state somewhere here. And depending on the sign of lambda 1, if it is positive, the state is going to go in that direction. This is lambda 1 is greater than 0. If lambda 1 is smaller than 0, the state is going to be going in that direction. Okay? The similar thing is correct for the other eigenvector. So depending on the sign of the eigenvalues, starting the state on these lines would give us trivial trajectories. So the state cannot escape from this line when it is started on one of these lines. All right? We are going to consider our investigations in two parts. The first investigation is going to be the case of real eigenvalues. When both of the eigenvalues are real, our system trajectories would behave in a very straightforward way. So here, if the first eigenvalue is positive, then we are going to have that the motion is going to be in these directions. If the second eigenvalues are also positive, we're going to have motion like this. And what happens if I start the state somewhere here? In that case, it's not really obvious, because obviously, since this is not an eigenvector, the velocity of the state might be different on this line than this line pointing to this vector. So that means that if I start the system on this line, then the future time instance, the state might leave this line, because it's not the line is not corresponding to any eigenvector here. Okay, so the motion not on these lines would be slightly more complicated than the motion on these lines. Okay. And actually what we're going to do when the state is not on this line, on any of these lines, we are going to try to decompose the state into two parts. The first part is going to be on this line, and the second part is going to be on this line. Okay? Then we're going to propagate these components, and then we're going to combine them once more. All right? So this is going to be made by a state variable change in the original linear system. So the first thing that we consider is case 1. When lambda 1 and lambda 2 are both real. Okay? By the way, they are both real or they are both complex. Okay? We cannot have the situation here, one of them is being complex and the other one being real. Why is that? Because we started with an A matrix which has all real elements. Okay? If A matrix contained complex elements, then one of the eigenvalues might be complex and the other one might be real. But if the A matrix is composed of only real elements, then when I have one of the eigenvalues a complex eigenvalue, then the other one is going to be its complex conjugate. Okay? Because so if the matrix A has real components, has real elements, then the characteristic polynomial would be a polynomial with real coefficients. And real coefficient polynomials would always, if they have a complex root, then the complex conjugate of the same root would also be another root of that polynomial. Okay? That means that since A is composed of only real elements, when one of the eigenvalues is complex, the other one is going to be complex as well. Or when one of them is real, the other one will be real as well. Okay? So let us say that our system is in the following form. X dot is equal to 0, 1, minus 3, 4, x. This is my system. And let us consider this system and try to draw its trajectories. The first thing that I'm going to do is to find the eigenvalues of this matrix here. So I have A equals to 0, 1, minus 3, 4 here. Let us calculate the eigenvalues. The first thing that I do is to calculate the matrix Si minus A. And it's going to be S minus 4, minus 1, and 3 here. And the characteristic polynomial, d of S, is going to be the determinant of this matrix. Determinant Si minus A. And we see that it's going to be S squared minus 4S plus 3. So now this can be factorized as S minus 1 and S minus 3. Now I see that the first eigenvalue will be 1 and the second eigenvalue would be 3. Okay? I can actually take the reverse situation as well. It really doesn't matter. So now I'm going to find the first eigenvector corresponding to the eigenvalue lambda 1. All right? In this case, I will write A minus lambda 1 identity. I know that the eigenvector is going to be a non-zero vector, which is going to be in the null space of this matrix. Okay? This is A minus identity, so I will subtract 1 from the diagonals here. And that is going to give me minus 1, 3, 1, and minus 3. Okay? Eigenvector E1 is going to be a non-zero vector, and when I multiply that non-zero vector with this matrix, the result has to be equal to 0. All right? Eigenvector is going to satisfy this equation, lambda 1 identity times E1 is equal to 0, while E1 is not equal to the 0 vector. A non-zero vector which multiplies this, and I would get 0. So what vector do you think it can be? By the way, if I find an eigenvector, any non-zero multiple of that eigenvector would also be an eigenvector. Okay? So if I find the vector E1 as an eigenvector, then 2E1 is also an eigenvector. Okay? Or 5E1. So here I see that a non-zero vector, when I multiply this matrix with, would give me 0 if that non-zero vector can be 1, 1. Okay? So this is going to be my first eigenvector. This is for lambda 1 equals to 1. And let us consider lambda 2. A minus lambda 2 identity, subtract 3 from the diagonals of this matrix. Minus 3, 1, and minus 3. And find a non-zero vector that would give you the 0 vector when you multiply it with this matrix. And that is going to give me E2 equals to, I would write 1 and 3. Okay? When I multiply this vector with this matrix, it's going to give me 0. This is a non-zero vector. That means that this is an eigenvector. Okay? And this is the other eigenvector, or lambda 2 equals to 1. Sorry, lambda 2 equals to 3. All right? So now I have found my eigenvectors with the eigenvalues. So now I can actually start drawing a little bit what the phase plane would be looking like. I have x1, x2 here. My first eigenvector has equal components. So the line corresponding to that eigenvector would be this line, okay? And what about the other eigenvector? The x1 component is 1 and x2 component is 3. So if I take the value 1 here, I need to take the value 3 here, okay? Sorry, maybe I should draw it to scale a little bit. So this is 1. So this is x1 equals to x2 line. So if I take x1 1, x2 1 is going to be here. It's 3 times this one. So I would take this point. So the eigenvector line is going to start from this point. It's going to pass through that point, and it's going to give me something like this. Sorry. So I have the line corresponding to the first eigenvector, E1, and line corresponding to the second eigenvector here. Now, what do I do about the motions? If I start my state somewhere here on this line, then I know that the state is going to diverge towards infinity, okay? So on this line, the motion lines are going to be pointing away from the origin. They would be pointing towards infinity. Okay? So on these lines, the motion would be away from the origin and going towards infinity in both cases. And what about the other one? The other one would be similar. Okay? And I would have motions given like this. So when I start state on this line, state will remain here, but it would diverge towards infinity. And similarly for the other eigenvector. All right? But the question here is, what happens? What happens when we start a state somewhere other than on one of these lines? Okay? What is going to happen when we start a state somewhere here, for example? How would the motion of the state or the trajectory of the state would behave? So here, in order to be able to understand the behavior of the system, somewhere not on this, started somewhere not on these lines, we are going to be defining a new state vector. Okay? And here is what we are going to do. So I'm going to define new state coordinates, and I will try to examine the motion of the state on these new coordinates. Okay? So here is what I'm going to do. Originally, if my state is here, I would investigate this by the x1 component and the x2 component given here. Okay? So this is my x1 and this is my x2 component. And this is my state x. Okay? Now, in order to be able to investigate the behavior of the state on somewhere here, I am going to change my state coordinates from these lines, x1 and x2, to these lines, which would correspond to the eigenvectors. Okay? So here, instead of examining this state according to its x1 and x2 components, I will try to decompose this state into two parts. The first part is going to be this part. Okay? And the other part, it is going to be this one. All right? And the sum of these components would give me again the same state. Okay? I will call this component as Z1, the length of this component as Z1, and I will call the length of this component as Z2. Okay? So these are going to be my new coordinate axis. This is going to be my Z1 axis, and this is going to be my Z2 axis. Okay? Instead of examining a state vector x in terms of its x1 and x2 components, I'm going to instead examine the same state x in terms of its z1 and z2 components. Okay? How would we do this? So what I would like to do is to write any state value x. I would like to write any state x in terms of two components, z1 and z2. In general, you know what we do. This is x1, x2, okay? And we examine this as x1 times 1, 0 plus x2 times 0, 1. This is my x1 axis component. It is this vector, x1 axis, and this is x2 axis. This is x2 axis, 0, 1, okay? Here is what I would like to do. So instead of so this is my 1, 0 vector, and this is 0, 1 vector, and we are examining an x as x1 times this vector plus x2 times this vector, and then the sum gives me x. Now instead of doing that, what I would like to do is I would like to express my x as z1 times this eigenvector plus z2 times this eigenvector. Okay? We know that our new axis here would correspond to the eigenvector E1 and E2. So what I would like to do is to write x as the first new axis component z1 times E1 plus z2 times E2. Okay? I would like to express my state vector in this form. And we know actually this is a function of time. X is a function of time. Then z1 is going to be a function of time. E1 is constant. And z2 is going to be a function of time. And E2 is a constant. Okay? This would correspond to a state vector change for us. Alright? So if I write the state z, this is going to be my new state vector, and it's going to be composed of z1 and z2. Alright? Suppose that I try to write this x in terms of this new vector. X is going to be my first eigenvector, my second eigenvector, and I would have the vector z here. When I put this vector z1, z2 here, this is z1, z2, you see that x is going to be z1 times E1 plus z2 times E2. I will call this matrix as the matrix P. Alright? That is our matrix P. Now that gives me the state vector change. So this is a constant matrix, P times Z. Or I can write Z equals to, since these eigenvectors are linearly independent, this matrix is going to be invertible. So I can say Z is equal to P inverse X here. These two expressions are equivalent. All right? So what is going to be my P matrix here? My P matrix is going to be composed of the eigenvectors as its columns. And the eigenvectors are 1, 1. And this is the first eigenvector, first column. Second eigenvector, 1, 3. This is my P matrix. What is P inverse? It is going to be the 1 over determinant. I would have 1 over 2 times 3, 1, minus 1, minus 1. Okay? So we are changing our state variable from x to z. And z is given in terms of x as P inverse x. And x is given in terms of z as P times x. So now let us try to make this state vector change here. We are changing our state vector axis from x1 and x2, these two orthogonal axes, to these axes. These two axes are no longer orthogonal, and the components of x on this axis would be z1, and component of x on this axis would be z2. Okay? So now let us try to change the state vector on this system equation. X dot is equal to ax. Okay? I want to obtain the new dynamics of the system. I need to write the new dynamics. Z dot is equal to, there will be a new A matrix that is going to be called A bar Z. Okay? I need to make the state conversion from here to here. So let me start with Z dot. Z dot is, Z is equal to P inverse X. P is constant with respect to time, so P inverse is constant with respect to time. So when I take the derivative of both sides of this equation, it would give me P inverse times X dot. And I have P inverse, X dot is A times X. It gave me this. But I want to get rid of this x from here because I want to obtain something like this. On the right hand side I need z. So for that I use the first equation, x equals to p times z. That is going to give me p inverse a p z. Okay? So you see here that if I write this equation as z dot is equal to a bar times z, the state equation or state matrix here in the new coordinates would be a bar, and a bar would be equal to this, p inverse times a times p. Okay? So let me try to calculate this matrix for our example. So P was given like this, P inverse was given like this. So let me calculate it for our example. P inverse is that matrix, 1 over 2, 3 minus 1, minus 1, 1 here. Okay? And A matrix, it was 0, 1, and what was the matrix? What was the second row? Minus 3, 4. Minus 3, 4. And the P matrix itself. So 1, 1, 1, 3. So now let us do this multiplication. 1 over 2. 3 minus 1, minus 1, 1. Multiply these two matrices. 1, 1 is going to give me 1, 1. And 1, 3. So this is going to be 3, and 12 minus 3, 9. Now let us do this multiplication, 1 over 2, 1, 1, it is going to be 2, 0, and this one would be 9 minus 9 would be 0, and 9 minus 3 would be 6. That's going to give me, divide everything by 2, it's going to give me 1, 3, 0, 0. This is my A bar matrix. So we see that this A bar turned out to be diagonal, 1, 3. This is not actually a coincidence, okay? So if you remember a few years back, when you learned linear algebra, this type of operation is called the diagonalization of a matrix. And in general, you should know what those diagonal elements are. And you see that they are nothing but the eigenvalues of the matrix, lambda 1, lambda 2, okay? So here we achieve diagonalization, and what is this going to mean? Let us put them into the equation for z. So that tells us z dot is equal to this diagonal matrix 1, 3, 0, 0, z. You see that when I write the individual differential equations corresponding to the matrix, the vector differential equation here, I will write z1 dot is equal to z1 and z2 dot is equal to 3z2. These are the two differential equations corresponding to this single vector differential equation. But you see here that these two differential equations are now decoupled. What does that mean? That means that the Z1 differential equation does not depend on Z2, and Z2 differential equation does not depend on Z1. So I have started with two uncoupled differential equations. If you look at the differential equations corresponding to the original system, you would get, with this A matrix, you would get x1 that is equal to x2, and x2 that is equal to minus 3x1 plus 4x2. You see that these differential equations are highly coupled differential equations. x1 differential equation is dependent on x2, and x2 differential equation depends on x1. But you see that in the new coordinates, in the original coordinates, the differential equations are coupled. But in the new coordinates, when I take my z1 vector here and z2 vector here, then the differential equations become uncoupled. Okay? This is very good because I can actually individually solve those one-dimensional differential equations. These are first-order scalar differential equations and very easy to solve. What are their solutions? This tells me that z1 of t is equal to z1, 0, the initial condition for z1, and e to the t, and z2 of t is equal to z2, 0 times e to the 3t. Okay? So you see we could write their solution. But on the other hand, trying to solve this it really would not be meaningful analytically here. So then I have these two equations. Now I can substitute them back into my x solution. Okay? So here, maybe I need to get rid of these instead. So I'm going to substitute them back into my equation here. X of t is equal to z1 of t, which is this, z1, 0 e to the t times the first eigenvector plus, and z2, 0, the initial condition for z2, e to the 3t times e2. What does this tell us? This tells us the following. Suppose that I have my initial condition here. The first thing that I'm going to do in order to be able to obtain the solution is to decompose this into these eigenvectors. Okay? And as soon as I decompose the initial condition into these eigenvectors, those are going to give me, the length of those vectors will give me z1, 0 and z2, 0. Okay? Then what is going to happen? The component along the direction of E1, this component here, this initial component, is going to grow exponentially with the eigenvalue 1, lambda 1 equals to 1. This is going to grow exponentially, okay? This component is going to go towards infinity. And what about the other component? The other component is going to grow to infinity as well, okay? But it is going to have the exponent 3t here. So this component is going to go to infinity as well. But these are these individual components. Then how am I going to obtain my solution x? My solution x is going to be the summation of those two growing components. Okay? So this component is going to grow. This component is going to grow. Which one is going to grow faster? I know that Z2 component is going to grow faster because it has e to the 3t. Its growth is with a higher rate than the growth rate of the first component. Okay? And as a result, this component would be growing with speed 1. This component would be growing with speed 3. So the component on the left is going to go much further away than this component. Okay? Then that means that such an x is going to make a motion in the following manner. It is actually going to start like this, but then it's going to go parallel with the component growing with the faster speed. All right. So how can I be sure about this type of behavior? So let me try to draw the trajectory of my system in the Z1, Z2 plane. Suppose that I take this axis as Z1, and suppose that I take this axis as Z2, and I decouple them, and I make them orthogonal, and suppose that this is Z1, and this is Z2. How would the motion of the system would be on Z1, Z2 plane? If I can draw the motion on the Z1, Z2 plane, then I would take these axes, then I would make them closer, and I would put it onto the x1, x2 axis, and would try to see the original motion of the system. Okay? So let us try to obtain the motion of the system in Z1, Z2 plane. So these are my two equations, and I need to express Z2 in terms of Z1 to obtain the phase plane trajectory on Z1, Z2 plane. Okay? So let us get those equations. The first equation I can write as follows. Z1 of t is over Z1, 0 is e to the t. And the second equation I can write it as Z2 of t over Z2, 0 equals to e to the 3t. So now I want to get rid of time from both of these equations, and I need to get a single equation relating Z1 and Z2 together only, without time here. So here I will remove these times here, and I would get rid of these time components from these equations. So here's what I'm going to do. I am going to take the cube of this first equation, and I would have e to the 3t. But you see that now the right hand sides are equal. That means that I can equate the left hand sides as well. So Z2 over Z2, 0 is equal to Z1 cube over Z1, 0 cube. Now just take this Z2, 0 to the other side. It's a constant. It gives me Z2, 0 over Z1, 0 cube times Z1 cube. So this is the equation relating Z2 to Z1. Okay? Now I can use this equation to be able to actually draw the trajectories of the system on Z1, Z2 plane. So this is just a constant, okay? So Z1, 0, Z2, this is just a constant depending on the initial conditions. So think of this equation just like this. Z2 is equal to gamma Z1 cube, all right? Where gamma is determined, is a constant determined by the initial conditions, okay? So if I try to draw these trajectories, if gamma is positive, we're going to have a trajectory like this, Z1 cube. So it's going to be a convex curve. And I would have Z1 cube, it's going to be a concave curve when we have negative Z1, like this. And if gamma is negative, then I would have the other types of curves, okay? And what about the trajectories on these lines? Suppose that I start my system here, okay? What does that mean? That means that, so the initial condition of the system is a non-zero component for Z1, 0. This is non-zero and positive. If I start the system here, this is non-zero and positive. Z1, 0 is non-zero and positive. And Z2, 0 is just 0 on this line. So this is 0 here, okay? So we see that if I start the system here on this line, then Z2 is going to be 0 forever, because Z2, 0 is 0. So I have just 0 for Z2, and that means that the trajectories of this system on this line would always remain on this line. Okay? And Z10 is positive, and that means that Z1 of t is going to be diverging towards infinity. So on this line, the trajectories would be towards positive infinity. Why did this happen? Because this line, this Z1 line, corresponded to the first eigenvector in the x1, x2 plane. And you see what is the motion on the x1, x2 plane. It is just like this. So if I started system on the Z1 axis, the trajectories would remain on the Z1 axis. What about Z2 axis? I know that a similar thing is going to happen on the Z2 axis because eigenvalues are both positive. All right? And what happens on the other lines? On the other lines, the trajectories would be diverging towards infinity like this. Okay? And here, there is going to be the equilibrium point of the system. If I start the system there, then that means that both Z10 and Z20 are 0, the system would remain here forever. And what about so this is where, if I start the system here, it's going to go on this line towards infinity like this. What about here, if I start the system here? What is going to happen? A similar thing is going to happen. So the trajectory would be looking like this. If I start the system here, trajectory would be looking like this. Why are these lines becoming parallel to the second axis? Why are these lines becoming parallel to the second axis? Because we know that the increase in Z2 is much larger than the increase in Z1. So when I start the system somewhere here, the initial conditions would be here and here, but this component would be growing much faster than this Z1 component, which would grow more slowly. All right? That is why these lines are always becoming almost parallel to the Z2 axis. This is because eigenvalue 2, which is 3, in magnitude larger than the eigenvalue 1, which was 1. If the eigenvalues reverse their position, if eigenvalue 1 was 5 and this was still 3, then these lines would be concave. Okay? Then Z1 increase would dominate Z2 increase, and then these lines would be almost parallel as time goes to infinity to the Z1 axis. All right? So these are the trajectories on Z1, Z2 plane. So then I will ask the following question. What is going to happen to the original motion when I go back to the x1, x2 plane? If I try to draw the trajectories here on this x1, x2 plane, what is going to happen? How the trajectories would look like in that case? And the answer to this question can be visualized by imagining to take these lines away, take this figure away from the board, and then bring the axis closer so that these axes would look like these, and then placing the figures just on top of here with the similar parabola here. Okay? And if you do that, you're going to see some trajectories like this. A trajectory given like this, another one given like this. And if you try to draw the trajectories, so the trajectory lines would be looking like this here. And we already have drawn the trajectories on these eigen lines here. And what about the trajectories on the other side? So if I start the system somewhere here, what is going to happen? This point is going to correspond to maybe a point. So I'm going to decompose this into two, and you see that this corresponds to a positive Z2 and a negative Z1. So this is going to correspond to a point somewhere here. So if you try to draw a trajectory starting from here, you're going to need to do something like this. Okay? So this is going to be surprising at first. So I would have drawn something like this. Why are these trajectories like this? Why are they behaving in this manner? They are behaving in this manner because a trajectory started here is always going to end up almost parallel to the Z2 line. And remember, this is my Z2 line, okay? And the trajectory starting here is always going to end up parallel to the Z2 line, which is going to be this line. And if I try to draw the other ones, they're going to be looking like this. So these are the trajectory lines, and they would be looking like this. And what about these ones? These ones are going to be, so this is this quadrant here. And you see that the trajectories here are always ending up parallel to the negative Z2. And this is negative Z2 in x1, x2 plane. And that means that if the trajectories are starting somewhere here, they are always going to end up parallel to this line. Okay? So this is how the trajectories of a simple linear system would be looking like. And in order to be able to end up with such a figure, we have drawn first the trajectories in the new coordinates Z1 and Z2, and then we have passed them into x1 and x2 coordinates. So in the next lecture, we are going to try to do the similar thing for the more general case. So we are not going to be given the A matrix in the next lecture. We are just going to be given its eigenvalues and possibly eigenvector directions. Then we are going to try to draw the trajectories in a similar way. So just as an example, if the first eigenvalue is positive and if the second eigenvalue is negative, in that case, what type of motion would you expect? If the first eigenvalue is positive, then the motion is going to be like this. So on this line, we would still diverge towards infinity. And if the second eigenvalue is negative, suppose instead of 3, I had minus 3 here, you see that Z2 would be converging to 0. Okay? So on this line, the motion of the trajectories would be looking like this. Okay? What is going to happen when we are on none of these eigenvectors? We're going to see that in that case, the motion would be quite different than this parabola, and instead the motion would be looking like this. Okay? Just like 1 over x type of behavior. Okay? And the directions here would be fitting the directions on these axes, and here there would be the equilibrium point. And now, if I want to draw the trajectories on x1, x2 plane, I would do this. This is x1, x2. Suppose this is my first eigenvector. Suppose this is my second eigenvector. Then the motions would be on these eigenvector lines would be like this. And here, on this one, I would have these. And then the trajectories would be looking like this. Okay? And this one like this. This one like this. And finally, this one like this. All right? And I have the equilibrium point here. When we investigate linear systems in this manner, we are going to name the eigenvalues, name the equilibrium points like this or like this with different names. You see that the trajectories around this equilibrium point would be quite different than the trajectories around this equilibrium point. So that is why we are going to give different names to these equilibrium points, to these isolated equilibrium points of linear systems here. We are going to call this equilibrium point a node. And the property of a node type of equilibrium point would be that the eigenvalues are going to be real and they are going to have the same sign. So here in this example, eigenvalues were real and they had the same sign. They were both positive. In that case, we would name this equilibrium point to be a node type of equilibrium point. So I will call this a node. And you see that the trajectories are always diverging from this equilibrium point. So this is going to be an unstable node, because the trajectories are diverging away from the equilibrium point. If both of these eigenvalues had negative sign, then all of the trajectories would be converging towards the equilibrium point. In that case, I would have named this equilibrium point to be a stable node. This type of equilibrium point, on the other hand, is going to be named as a saddle point. And saddle point is going to have the property that both eigenvalues are real, but they have different signs. And we see that here on one of the eigenvectors, we have diverging motion. On the other, we have converging motion to the equilibrium point. These are going to be saddle point. And a saddle point, since I have always a positive eigenvalue in a saddle point, is always going to be unstable. All right? And we are going to have, in the coming lectures, we are going to have a third type of equilibrium point and a fourth type. And these are going to be coming from the cases of complex eigenvalues. So we are going to have two different types of equilibrium points, which are called center and focus. In these cases will be classified according to the complex eigenvalues of the matrix A. So this was just a linear case for a specific example, the real eigenvalue case. In the next lecture, we're going to try to do the same thing for a general A matrix with arbitrary eigenvalues and arbitrary eigenvectors. But that is going to remain, it has to remain for the next lecture. Thanks a lot for watching. Bye-bye.